Let's look at trig-related rates class examples. For number 1, A and B should be familiar. It's just with part C, this is where we're going to have to require trig function in order to solve. So a ladder 50 foot long is being pushed against the wall at a rate of 5 feet per second. When the bottom of the ladder is 30 feet from the wall, what is the velocity at the top of the ladder? Okay, so if we can kind of visualize this problem in motion, the ladder is staying constant, so this h is never changing. Now we push this ladder towards the wall, we know that x is going to get smaller, so we know that the rate of change for x is going to be negative because it's getting shorter, but then the y value should be increasing because as the ladder gets pushed towards the wall, the height of the ladder is going to move up the wall. So we know that the y is going to increase over time. So we know that the rate of change for y, the dy dt portion, will be a positive value. Right? So we list out all the variables that we may or may not need. So x, y, and h, dx dt, dy dt, and dh dt. And h is 50, but the rate of change for that ladder is going to be 0. It's not going to change over time. X is equal to 30. Okay? It says when the bottom of the ladder is 30 foot from the wall, and then we know that at that moment in time, y is going to be 40, okay, using Pythagorean theorem. And we know dx dt is negative 5 feet per second because the ladder is again being pushed against the wall, meaning that this distance will be getting smaller over time, so we're going to have to require a negative value. Okay, negative is not dependent on the direction; it's dependent on whether that value is decreasing in length or whether it's increasing in length. In this case, it's decreasing in length, so negative. And we're trying to solve for dy dt. Okay. Now, the equation that relates these variables together is Pythagorean theorem, right? X squared plus y squared equals h squared. Find the derivative of each variable with respect to time. So 2x dx dt, 2y dy dt, 2h dh dt. And this dh dt is 0, so we know that the right side will be equal to 0. We can fill in all the other information, including the x, the dx dt, the y, the dy dt. And then we just take steps to solve for dy dt, which will be 3.75 feet per second. Okay, part B. At what rate is the area of the triangle enclosed by the ladder, wall, and floor changing? So now the equation that relates the variables is area. Area of a triangle is 1/2 base times height, and the base is represented by x, the height is represented by y. And if we want to find a derivative, we got to go through product rule, right? I'm going to treat 1/2 x as my first function and y as my second function. So product rule, we can use f prime g plus f g prime. Okay. So our derivative, f prime, is 1/2 dx dt. My g is y. My f function is 1/2 x. My g prime, the derivative of y is 1. We attach dy dt. Okay. We know dx dt is negative 5. We know y is 40. We know x is 30, and we know dy dt, which we just found from part A, is 3.75. So plug this in your calculator. It'll get you negative 43.75 square feet per second. Right? Unit of measurement is rate of change of area, so square feet, and then per second. Okay. Part C, at what rate is the angle formed by the ladder and the floor changing at that time? So we're trying to find the rate of change of theta. So first we need to identify the equation that relates this variable with the other sides. So we're going to use sine. Right? Sine of theta is equal to y over 50. Okay. We could have also used cosine, but I'm just going to stick with sine here. We know information about y and dy dt, but technically we could do cosine and work with x and dx dt. Okay. The result will be the same. So sine of theta is equal to y over 50. I'm going to rewrite this as sine of theta is equal to 1 over 50 times y. Okay, now we go through our derivative rules. Sine of theta becomes cosine of theta, but because we're involving theta's derivative, we got to attach d theta dt. 1 over 50 times y becomes 1 over 50, and y becomes 1, but we attach dy dt. I'm trying to solve for d theta dt, so I'm going to divide both sides by cosine of theta. So I get dy over dt over 50, because 50 is in the denominator. The cosine of theta also shares that denominator space. We don't know what theta is, but we do know what cosine of theta is, right? We know that cosine of theta at this moment in time, we can look at the ratios of the sides. So the ratios of sides, cosine of theta is simply going to be adjacent over hypotenuse, so 30 over 50. Okay, so 30 over 50 will be the ratio for cosine of theta, and we can use that to cancel out. These cancel out. 3.75 over 30 is 1/8, and then this tells us the rate of change of theta, so 1/8 radians per second. Okay, number 2, a television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to S of t is equal to 50t squared. So this tells us the y value at any moment in time for this for the rocket moving up. S is in feet, t is in seconds. Find the rate of change in the angle of elevation of the camera, shown below at 10 seconds after liftoff. So if we look at this diagram, we can write any trig equation that relates these three pieces of information. So tangent of theta is used to relate the s and the 2000. Okay. This 2000 is not changing, the s is changing, so we leave that as a variable, s over 2000. And we derivative, right? Tangent of theta becomes secant square of theta. S over 2000, we can think of it as 1 over s, which is 1 over 2000 times the derivative of 1, but we attach ds dt. Okay. Now we're going to do some work with our equation s of t, because we have to figure out what ds dt is to plug in. And then we also need information about theta, or a secant of theta, so that we can eventually solve for d theta dt. But let's do this then. Let's get d theta dt by itself first. So divide both sides by secant square theta. 1 over 2000 times secant square theta times ds dt. To make it a little bit easier, I'm going to bring the secant squared up and deal in terms of cosine squared. It's a little bit easier to think in terms of cosine. So now we have to kind of look back and see if we can figure out some of this information. So we look at our s of t information. S of t is 50t squared. So at this moment in time, if I plug 10 into my position function, my height is at 5,000. So 10 seconds, if we take a snapshot of this this problem, after 10 seconds, the rocket would be 5,000 feet above ground, right? And then, but ds dt, which is s prime, we're going to need this information for to plug in to find d theta dt. ds dt, since s of t is 50t squared, the derivative of 50t squared is just going to be 100t, and if I plug in 10, then I know that my ds dt at 10 seconds will be 1,000 feet per second, which we will use a little bit later. This moment in time, we know that the y value is 5,000, the x is 2,000. So if I want to find the h value, I can use Pythagorean theorem, and it's going to give me something a little bit ugly here, 29 million, square root of 29 million, which we'll plug in here. Okay. And if we go back to our problem, trying to solve for d theta dt, we know ds dt, which we just found to be 1,000 feet per second. But we need to figure out what cosine of theta is. So that's why this triangle is helpful. We don't know what theta is, but we know cosine of theta is adjacent over hypotenuse, 2,000 over the square root of 29 million, right? Adjacent over hypotenuse. We plug all that in. This is going to be squared. So 2,000 over square root of 29 million squared times ds dt is 1,000. I just pulled the 2,000 as a denominator for the second fraction here. And then it's just a matter of trying to simplify. This comes out to be 4 million. The square root cancels out because of the squared, so now 29 million. 1,000 over 2,000 is 1/2. Cancel out the 6 zeros on the million from both the numerator and denominator, so I'm left with 4 over 29 times 1/2, which reduces to be 2 over 29 radians per second as my d theta dt.